Hi, hello everyone, and welcome to our session. We are very excited to be here at the KubeCon, Cloud Japan. And today, we'll talk about a topic we believe is very important for running Kubernetes cluster, new cache hierarchy for container images and OCI artifact in Kubernetes cluster using containerd. Let's start with brief introduction. I'm Toru, and the founder of Yoki CNCF Sandbox project, the keynote mentioned. And OCI, Open Container Initiative Maintainer. And he is Hidehito, and we are from Preferred Networks. And our team builds and maintains infrastructure for R&D in our company, making our Kubernetes cluster using Kubernetes cluster better is a big part of our job. And today, we are sharing some of our effort in that area. First, I'd like to describe our computing infrastructure where the software we introduce is running right now. We at Preferred Networks are an AI and machine learning company, and we've developed machine learning models like large language models and many solutions for the industries. These activities use our on-premise computing infrastructure. We have 3 Kubernetes clusters for production and several evolution and staging clusters. As a total, there are more than 400 Kubernetes nodes with 30,000 CPU cores, 300 terabytes of memory, and 2,000 GPUs. Also, we've developed and operating our own AI accelerator called MN Core. We handle almost everything with our AI chips from RTL to board designs, drivers, of course, Kubernetes device plugins, and graph compiler. So what were the main problems that we wanted to solve? We were facing 2 primary concerns that many of you might also find familiar. Firstly, the need to accelerate content startup. External research, such as the paper from Usenix, indicates that a large part of content startup time, often more than 76%, is consumed by pulling images. Also, the default container images we provide to our researchers are often quite large, frequent exceeding 20 gigabytes. Secondly, we aim to reduce cloud costs. Which has a direct FinOps impact. But even beyond public cloud, for our on-premise infrastructure, reducing cloud egress traffic is also an important goal to ensure network stability. Let's quickly review the basic of how container images are pulled in a standard Kubernetes cluster setup. As illustrated here, the kubelet running on each worker node communicate with a container runtime. In our case, typically containerd we are using by the container runtime interface. Through the interface, the kubelet tells it to pull the required container images from registries like Docker or others. Currently, when we talk about image caching in Kubernetes cluster, we typically have 2 main locations, as this diagram shows. First, there's a node local cache on each worker nodes. And second, there's the origin registry, which is the original source of the container images. The important point is accessing this origin registry usually means going over the network to external location, reducing in cloud egress traffic. The cloud egress traffic to the origin registry has several problems. As this slide highlights, it incurs monetary costs, especially in cloud environment where egress data is often built. Furthermore, there can be a bandwidth limitation or network congestions, which can slow down image flows and impact overall performance. So given these challenges with the current 2-tier system, we started to think, can we do better? Is there a way to introduce another layer of caching? Specifically, could we have a cluster-level cache, a shared cache within our Kubernetes cluster to reduce dependency on external origin registries? This diagram asks these questions. And the answer to that question is yes. The cluster-level cache we saw of is exactly what we developed. CIRC, which stands for Container Image Registry Cache. As you can see in this updated hierarchy, CIRC sits between the node local caches and the origin registries. So what was the result? With CIRC, we made a pod startup faster and greatly reduced data transfer. This bar chart shows a roughly 20% startup acceleration on a cache hit. We also achieved a cache hit rate of over 98%, saving around 23 terabytes of internet data transfer in just a week. So how did we achieve this? Okay, now let's dive into the detail with Hidehito.
Thank you, Toru. So I represent our solution that brings this outcome. We call this system CIRC. CIRC introduces a new cache hierarchy level and improves container image caching with this additional layer. This additional cache is shared cluster-wide, so cached images are available for pulls from all nodes. When containerd pulls an image, the image pull request will go to CIRC. If the image is cached, CIRC immediately returns it to containerd. Otherwise, if the image is not cached yet, CIRC pulls it from the origin registry, stores it to the cache, and returns it to containerd. Until the cache is evicted, the same image is pulled from the origin registry only once. So most image pull requests are done within the fast in-cluster network. For the cache storage, we use SCS. SCS is a distributed cache service on our Kubernetes clusters, and it offers simple key value store functionality. We introduced SCS at the last year KubeCon North America, so please scan the QR code and check out the session for the details of SCS. While we use SCS, CIRC can work in an environment that does not have SCS. For example, you can use a file system or other implementations as cache storage. CIRC has high compatibility because it adheres to industry standards. CIRC implements OCI distribution specification, a protocol for distributing container images over HTTP. This protocol is standardized by OCI, Open Container Initiative. All major registries implement this specification, and CIRC also implements it. So CIRC continues working steadily when we upgrade containerd. That's the overview of how CIRC works. So next, let's explore CIRC features. I will talk about 4 features: transparency, multi-tenancy, preheating, and OCI artifacts. Let's dive in. First is transparency. Transparency means that users benefit from CIRC without needing to care about it. To ensure the transparency, we needed 2 things. First is no Kubernetes manifest changes are required, and the other is CIRC should work with arbitrary registries like Docker Hub or Quay. How to achieve the transparency? We use containerd's registry configuration feature. Registry configuration feature allows us to redirect requests to a registry to another server. In the example configuration file shown, request will go to CIRC, HTTP CIRC internal. Underscore default is a special registry name that matches any registry. So requests to any registry will go to CIRC. So with this configuration, Containerd will pull all images through CIRC. Let's walk through the flow of an image pull request. Let's consider a pod using an image from query.io. Containerd sends an image pull request to CIRC because it's configured to redirect all requests to CIRC. CIRC receives the request, and if the image is cached, CIRC immediately returns it. But if the image is not cached yet, CIRC tries to pull the image from an origin registry. But a problem occurs here. Where to pull the image from? How can CIRC know which is the origin registry? Containerd offers a solution. Its registry configuration feature tells CIRC what is the original registry via NS query parameter. Containerd sends HTTP request to CIRC with NS equal query.io because the pod is requesting an image from query.io in this case. CIRC reads this NS parameter to identify which registry to pull the image from. This mechanism enables CIRC to work with arbitrary registries, not predefined one. That's how CIRC achieves transparency. So next feature is multi-tenancy. CIRC's cache is shared cluster-wide. This increases the cache hit rate. But if the cluster is shared by multiple tenants, we must consider the security of shared cache. We must ensure that Team A's pod cannot use Team B's image in the cache unless the Team A's pods have enough permission. How can CIRC ensure secure cache sharing among multiple tenants? CIRC ensures secure cache sharing by enforcing authorization for cached images. Specifically, it first queries the origin registry whether the user can use the image by sending HTTP head request. Then, if the request is authorized, CIRC returns the image to Containerd, and otherwise, CIRC returns a not found error. By enforcing authorization, CIRC ensures secure cache sharing while increasing the cache hit rate. The third feature is preheating. CIRC returns images to Containerd quickly, but it is true only when the images are already present in the cache. New images need to be pulled once. But what if we could eliminate pulls altogether? We could speed up the first pull from Containerd. CIRC enables this optimization by supporting image push operations. When users build an image, they can push the image to CIRC directly, not to the origin registry. CIRC stores the received image to the cache storage, and it also uploads them to the origin registry at the same time for persistency. This push protocol is included in the OCI distribution specification and CIRC implements it. So various clients can push images to CIRC. Users push an image to CIRC, and afterwards they will request the image. Image pull requests go from containerd to CIRC. Since the image is already stored in the cache storage, the pull should be completed quickly, even if it's a fast pull. The last is OCI artifacts. OCI volume source feature is being developed in the Kubernetes and container runtime community. This feature allows pods to mount OCI artifacts. OCI artifacts expand the concept of OCI image. OCI artifacts are any content stored in the OCI image format. The use case of OCI volume source feature include distributing AI models, which can be huge, which can be dozens of gigabytes. OCI artifacts are pulled from container image registries, so it is great if we can pull them quickly. CIRC works for OCI artifacts as well. OCI artifacts follow the OCI image format, and CIRC implements OCI distribution specification. So with CIRC, we can pull huge AI models quickly. CIRC handles OCI artifacts, and this will contribute to foster the OCI ecosystem. Okay, I have introduced CIRC's 4 features: transparency, which means users benefit from CIRC without needing to be aware of it; multi-tenancy, that ensures secure cache sharing; preheating, that supports pushing images for fast pulls; and compatibility with OCI artifacts. All these features are built upon containerd capabilities and OCI, the protocols standardized by OCI. Without containerd and OCI efforts, CIRC and its outcome wouldn't be possible. Here, let me reiterate the real-world outcome that these features have brought us. Pod startup time was accelerated by around 20%. Thanks to CIRC's transparency, users benefit from this speed increase without needing to be aware of CIRC. Data transfer was reduced by about 23 terabytes in a week. The high cache hit rate of over 98% is partly due to CIRC's preheating feature. Furthermore, while it's 23 terabytes currently, but we expect even greater efficiency with the utilization of OCI volume source feature. As a quick note, remember that these features can vary depending on the environment and workload characteristics. Okay, now I hand over to Toru again.
Thanks, Hidehito. Okay. What is the benefit of CIRC are clear. Building and running this system in the real world, complex Kubernetes environment was not easy. We encountered several interesting development problems and challenges that we had to address. And we'd like to share some of those with you now. The first big problem we faced is what we call the bootstrap problem. CIRC itself is typically deployed as a pod. So how do you know to pull the CIRC image itself? If CIRC is a main image proxy? Or what about other critical system pod like the CNI plugin, which need to start very early, possibly before CIRC is fully operational? This problem is most acute during node startup. So what this diagram shows is that CIRC is down. Fortunately, containerd has a fallback mechanism, as you can see on this slide. Even if CIRC is down, containerd can be configured to bypass the available mirror and fallback to pulling image directly from the origin registries. So the fallback mechanism we saw on the previous slide allows the image pull to eventually succeed by going over the origin registry. But we discovered a major problem in the practice. This fallback mechanism process was very slow, sometimes taking over 20 minutes, while the image would eventually be pulled. The delay was often too long, especially for critical system pods that need to start quickly. So why was fallback this so slow? The reason it was so slow was that the timeout for the fallback was fixed at 30 seconds per image blob. For large images with many layers, this 30-second timeout for each blob quickly added up to unacceptable delays. Furthermore, image pull within a pod node are serial by default. So to address this critical timeout issue, we investigated this problem and reported it to the Container community. Later, the community made an improvement that now let you set the fallback timeout yourself. This means administrators can set a much shorter timeout, ensuring that if CIRC is unavailable, Container will quickly fall back to the origin registry. This solved the long delay problem we had before. The second major operation challenge we encountered is the thundering hard problem. Let's imagine daemon set is updated. This action causes many pods across the cluster to request the same images to CIRC at the same time. As this diagram illustrated, these requests for an uncached image all arrived at the CIRC at roughly the same time. This large number of requests for the same data, if CIRC doesn't have image cached, is the beginning of thundering hard problem. Without a way to coordinate in CIRC, this situation led to a problem. As this diagram shows, CIRC itself might end up sending the same request many times for image A to the origin registry at the same time. So how do we address this at the cluster level? Fortunately, Kubernetes itself provides a mechanism for coordinate called lease object. Leases allows members of a set to lock shared resource and coordinate activity. We use this existing Kubernetes feature for a single flight mechanism to prevent the thundering hard. Let's revisit the base problem that leads to this problem with a daemon set. If image A is not in CIRC, without a coordination, CIRC might end up sending multiple identical requests to the origin registry. This is exactly what we want to stop. To manage this, CIRC uses a mechanism based on Kubernetes lease object I mentioned. When CIRC receives these concurrent requests for the uncached image A, CIRC will attempt to get a lease for image A. This is the first crucial step in our cluster-level single-flight solution. In this diagram, the orange request wins the race in this example and gets a lease for image A. This means only the orange request goes to the origin registry to fetch the image and create the cache. Meanwhile, the green request sees that the lock is taken. So it simply waits for the cache to be ready by orange request. Once the cache is loaded by orange request, the green request can get the image directly from our CIRC and the SGS cache. The result is simple. Only one request hits the origin registry. This is how we solve the thundering hard problem. With these challenges, CIRC started working well. Let's conclusion. Let's summarize our presentation. Our goal was to solve image pooling problem in our large-scale clusters. To do this, we introduced a new cache layer with CIRC. As we discussed, CIRC has 4 key features. Transparency, users don't need to change anything, like Ninja. Multi-tenancy for secure cache sharing. Preheating, so the first pool is much faster. And the support for OCI fact, which opened up broader use cases for the future. And what about the result in the real world? The results were great. We accelerated pod startup by about 20% on the cache hit. And we solved around 23 terabytes on internet data transfer in just 1 week. So by solving the bootstrap and the something hard problem, we built a fast and reliable image cache solution for large systems. Thank you very much. And any question? And we welcome your feedback by a schedule application. Thank you. Is there anyone? Okay.
Thank you. Thanks for a very interesting talk. Caching is always an interesting part of our field. Why did you decide to put the cache inside the cluster rather than as an external service that could then be shared between multiple clusters? Yeah, external cache, like a single shared cache for your entire set of clusters rather than having one per cluster.
For now, we don't consider the multiple cluster. Your question is your question is for multiple cluster?
Sorry, the question was, why did you put the cache inside the cluster rather than external to the cluster?
Oh, yeah, good question. So, of course, you can put the cache in an external cluster, of course. But in our case, we have a very fast internal cluster network. So we want to put the cache in our private cluster.
Thank you.
Thank you.
Thank you for interesting session. There are no level container image cache, but there are no cluster level cache in original Kubernetes. So why is it? Do you know the reason except the improving the maintenance cost?
Okay, good question. So to be honest, Containerd has already provided a solution using IPFS, peer-to-peer file system. However, we didn't mention in this slide, but it is hard to solve the GC problem in the cache, of course. So cache has a limitation storage, so we need to delete the cache. But in our case, SCS, we mentioned this slide, already has a feature to delete the cache automatically. So it is a hard problem to solve in real world, I think.
Okay, thank you.
Thank you for great talk. And I'm wondering, like, I understand, like, the cache is in cluster, but where actually cache is stored, like, it's in a runtime like a CIRC. Like, I'm wondering where actually cache is stored, because, like, I understand it's in cluster. But I just wondering, like, sorry, I misunderstanding, but I just wondering where actually cache is stored.
Thank you for the question. The cache is stored in the Kubernetes cluster. We use SCS as our cache storage implementation, and SCS stores stores data in SCS aggregates node local data medium and to provide cache service on Kubernetes clusters. So the cache data is stored on Kubernetes.
Okay, thank you.
Okay, is there any questions? Or the time is over, so thank you for listening. Or if you have any question, please welcome here. Thank you.